A quadratic function is a polynomial function of degree 2. So it's a function that I can write in the form f of x is equal to ax squared plus bx plus c, where I'm going to assume a is not equal to 0, otherwise I would be a linear or a constant function. So this is a quadratic function, so a quadratic polynomial function. Right, so what I want to do is explain kind of the fundamental aspects of these functions. I'm first of all going to do it by thinking about various important examples about how we can graph quadratic equations. So let's do a quick example that we're all familiar with for sure. Let's do the example of f of x is equal to just x squared. So this is a quadratic equation, of course, because it's degree 2. I remember it's a quadratic polynomial function, so this means degree 2. So this is a quadratic equation with a is equal to 1, b is equal to 0, and c is equal to 0. So the graph of this is something we've seen quite a few times now. It's an even function, so I have a symmetric graph after reflection across the y-axis, and it looks like this. So this is what the graph is. And this graph is called something. It's called a parabola. So the graph of any quadratic function as I said, is called a parabola. A parabola. Okay, so this base case, dead simple. Can we use it to graph, in theory, any quadratic equation? So this is an interesting question. So can we use this to graph any quadratic? So of the form y is equal to ax squared plus bx plus c. That's the question. So can I somehow leverage this graph to get any possible parabola? So to do this, I'm going to go through a process called completion of the square, something that I'm sure many of you have heard of before. I want to go through it really carefully by example before talking about the general picture. From experience, this is something people struggle with. It's a piece of algebra that's often very badly explained at high school. I'm going to go through it really carefully because it's going to be the key really to understanding the behavior of the graph and the behavior of the function overall. So observation. So if I was to give you an expression in the form x plus, let's say, capital D, where that's a constant squared. So of course I can FOIL this, and I would get x squared plus 2dx plus d squared. So as an example, if I had x squared minus 2x plus 1, this could be written kind of in a factored format if you want, x minus 1 squared. So let's just think about how I might spot this if I was doing this in practice. I mean, so I could factor this, but let's just imagine how things fit together. Okay, so here basically we have 2d is equal to minus 2. So that implies that d is equal to minus 1 in this picture. And you've got to be careful. You've got to make sure that fits with this piece as well, because I've only looked at this to get this d. And this, of course, implies that d squared is equal to 1. So it all fits together nicely. So unfortunately, we can't do this for every single quadratic. We definitely know we can't, which is a very special thing, having this repeated linear factor if you want. But it will still be useful. So while we cannot do this, we cannot do this exact algebra for every quadratic. We can partially apply it. So what does partially apply it mean? Well, let me give an example. So imagine if instead of this guy, I had this guy. So let's say x squared minus 2x minus 2. I should maybe say a reason I'm interested in this is because, well, if this is equal to this is very, very similar to x squared. In fact, it's a simple transformation of x squared if we think about it, right? It would be a translation to the right by 1, because you're replacing the input with the input minus 1. So this seems like a nice idea if I'm going to try to go from my x squared example to something else. But let's take this example at the bottom. And let's do the same kind of logic, right? So if I was trying to match this up with this pattern I've just got above here, what would I do? Well, exactly the same thing, right? We would have 2d would be minus 2, so I'd have to choose d to be equal to minus 1, and that would imply that d squared is equal to 1. But that's a bit of a problem, isn't it? Because that's a minus 2. It's not equal to d squared, so it doesn't fit the pattern. But is there some clever way I can get it to fit the pattern? Well, here's a really clever idea. Let's add and take away 1 to this. So this is kind of a bit of an algebraic leap of faith, but let's write this. So I'm kind of just, in this space, adding and taking away 1. This makes no difference at all. But if you think about what this really is, I'm adding and taking away d squared in this example. So this is kind of plus d squared and then minus d squared. So it doesn't alter anything because all I'm doing is adding 0. But the moment I've done this, the first 3 terms now fit this pattern above. They're exactly this. So now I can write them in the form x minus 1 squared. So what would this give me? This would give me x minus 1 all squared minus 1 minus 2, which would come out to be x minus 1 squared minus 3, right? So that's pretty neat, right? This means now I've written this expression in this format. And this format looks pretty sensible. Again, if I'm trying to get from x squared to this, because it looks like a type of function we studied when I was doing compositions of transformations. Remember, I was going from things like y is equal to f of x to a constant a plus b times f of cx plus d. I've got something very similar to that here. Okay, it's almost exactly the same. In fact, it is exactly the same for that specific format. So those are equal, right? Let's do another example. Okay, so imagine I was confronted with, I don't know, let's do this guy. Minus 2 x squared plus 4x plus 4. So what I'm going to do is I'm going to take out a minus 2 as a factor from everything. So I'm going to pull out a factor of minus 2. I've got to take a minus 2 out of everything. So this would give me x squared minus 2x minus 2. And notice that is exactly what we've just done, right? That is equal to all 3 of these. So this becomes equal to what? It will be minus 2, so I'll do a square bracket now. It would be x minus 1 squared minus 3 all together. So putting everything together would give me minus 2 times x minus 1 squared. What would it be? It would be plus 6, wouldn't it? So this expression, so let's just recap a second what we did. We first of all pulled out a factor of minus 2 here. Then when I did that, I've got an x squared plus something. Then I used this x plus d business, but I had to be careful because it didn't fit the bill exactly. That minus 2 was a problem, and I needed that to be 1. So to make it 1, I added 1 and took it away, kind of a funny little algebraic trick. Then I gathered this term into one piece here, and I just collected the back terms to give me this. All right, so why have I done this? Well, let me explain more formally than I did before. So we know the graph of y is equal to x squared, don't we? So what we need to do is go from this to the graph y is equal to minus 2 of x minus 1 all squared plus 6 in this example. So this is a classic, right? This is exactly the situation we've seen before, right? This is a y is equal to f of x, and I'm trying to get across to something of the form, what is it? Y is equal to a plus b f of cx plus d. It's exactly that type of situation. Right, so here a would be 6, b would be minus 2, c would be 1, d would be minus 1, and the function f would be x squared. So what we're trying to do is come up with transformations that go from x squared to this. So we're looking for transformations. So how does it work? Well, it's pretty delicate, remember. It all depends on the order you do things in. And there was an order that I gave us which was very safe, and I'm going to go through that order now. So first of all, we've got y is equal to, so let's give ourselves some reasonable amount of space. So we've got y, where am I? We've got y is equal to x squared. The first thing I do in the safe order, because it's fairly easy to read off, is horizontal translations. And it's pretty obvious I should be translating to the right by 1. So this is going to be y is equal to x minus 1 squared. That should be my first plan of action. So this is translate to the right. Translate to the right by 1. Let's draw a graph underneath it. Just let's keep a running graph all the way through. Just a small graph which we can understand what's going on. So here, this is my start guy. This is y is equal to x squared. So the next guy is translation. It's translation to the right. Let's just copy this whole thing. So this is translation to the right by 1, so it would be the following. Moving it over here. So this position here would be 1. That's the first step. Next, you do horizontal stretch compress. Do I need to do that? Well, no, thankfully, because it's a 1 in front of this. Next, I would do reflections across the y-axis. I don't need to do those because it's not a negative in front of x. Brilliant. Next, I need to worry if I'm going to do any reflections across the x-axis. I do, because this is a negative. So that should be my next thing I'm doing. Oh, there's a lot going on here, right? So we're going to reflect across the x-axis. So what is this going to do? It's going to turn the whole thing up on its side. Well, upside down, isn't it? So it's going to be upside down like this. It's a pretty bad parabola. Not bad. Okay. So in terms of algebraic expression for this, this is y is equal to minus of the entire output, that's minus x minus 1 all squared. Next, you do vertical stretch compress. It's the safe order. So it's minus 2, so we need to stretch by a factor 2 now because we've already got the negative. So I would do a vertical stretch by factor 2. Vertical stretch by 2. Algebraically, that gives y is equal to minus 2x minus 1 squared. So what does that give? It's going to kind of stretch it out. It's not so easy to draw. But it's going to be going over here. And it would be the following. But it's kind of going to be stretched out from the x-axis vertically, so it would kind of be thinner. Like that. And finally, what happens? Well, I need to translate up by 6, don't I? So I hope I can fit this. Just very tight in. Okay, so this now is translate up by 6. And that, of course, in the graph is pretty nice. It would just be moved up, wouldn't it? So we have exactly the same thing, but this guy gets lifted up to some position up here. So this would be the position 6 now. Okay, so this is really clever. This has allowed us to graph the quadratic equation given by this by rearranging it into a kind of a different algebraic form, namely this, and then using a series of translations, or transformations, sorry, to go from the core case y is x squared to what I'm aiming for. So this process, as I've already alluded to, is called completing the square. So it's a really lovely idea, and it will always work. So fact. This process will work with any quadratic function. Ax squared plus bx plus c. It'll work with anything. And it's called completing the square. So this process is called completing the square. So I don't blame you if you're looking at this and thinking, man, well, what is this process in general? I could follow it step by step for this, but what happens in general? So let me give you the general story. So here is the general setup for this. So here we go. And I should be careful, it works for any function. To be strict about this, it's got to be a quadratic function, so a can't be equal to 0. Otherwise this wouldn't make any sense. I suppose, yes, you have to do it with a as non-zero. So here is the general process. So we'll start with y is equal to ax squared plus bx plus c. So this is often called the quadratic function in standard form. The next thing we're going to do is factor out an a. So if you give me a little bit more room here. So factor out a. Just like we did with the -2 a second ago. So this is going to give you y is equal to, okay, so what would it be in general? A x squared, okay, plus b divided by a. Plus b divided by a plus, oh, times x, sorry. Plus c divided by a. Now the next thing is to take what's in this parentheses and write it in the format we did a moment ago. So the format we did a moment ago was, well, we had this, we had to write it in this format here. So this is the general format you want to do, so let's kind of carefully describe this. So we're going to write this, so write the term in parentheses in the form x plus d all squared, and I'll say plus k. So what's the basic deal here? You need to write this as 2d because you're doing an x plus d all squared. So when you fall that, you'll get an x squared plus 2dx. So when you do that, so I'm going to write down the general picture here. You would get y. So I hope I've got enough room to do this. Y is equal to, okay, we've taken the a out, then let's do a big square bracket. Then what goes inside? Well, it turns out the following. X plus b divided, so this is going to look pretty unpleasant, divided by 2a all squared. So you need that because this has to be your d. But then what happens is, well, when you multiply this out, you're going to get a b squared divided by 4a squared. So you've got to take that away from the story. So it's a bit of a mess. So you're going to have this minus b squared divided by, so this is b over 2a squared, 4a squared, and then you'd have to have plus c over a. So it's a bit of a mess, as I said. So I'm writing this down just to show you how it's done in general. You shouldn't memorize these formulas or anything like that. You should understand the process that goes into them. So this is the k. And then finally, well, let's kind of just make sure we understand what we're looking for. We put this in the format. So really what we're trying to do is the following. We're trying to put this in the format So we're trying to put this in the format y is equal to x plus d all squared plus b. That's the format we're trying to put it in. That's the format we saw a moment ago up here. It seemed to be very useful to us. And we've really done that at this point. So from here to here, you can read everything off. So I'll just read each piece. It's a bit of a mess. But A, capital A, is equal to little a, thankfully. It's pretty obvious, right? Because the x squared comes from here and you're multiplying it by a at the front. The d, we've just seen the d. So I should do this in red, shouldn't I? So the a is equal to little a, d is equal to b divided by 2a. We need that to get the linear piece. And then by far the biggest mess is this piece at the back, which is pretty horrid really. It's going to be equal to the following. So the b, I would need to multiply k by a, so it's a bit of a mess. When I do that, it comes out to be a multiplied by minus b squared divided by 4a squared, gross, plus c divided by a. So we're multiplying out by a there. So that overall process is called completing the square. Let's take the time to highlight this properly. So that procedure is called completing the square. So you factor out the a, then essentially you decide on your d, which is going to be a half of b over a. You write it in this format, and you've got to be careful because you've got to kind of counterbalance this, because this expression will give you a plus b squared over 4ac. You don't want that in there. That's why you've got a negative here. So it's a little bit of a mess, and that overall puts you into this final format. So I think this is quite a difficult procedure. It's called completing the square, like I said. Completing the square. It's kind of a funny name for it. I suppose it's because you're putting it in with a square format here, if you want to put it like that. So again, do not memorize these formulas. Do not do it, right? You shouldn't be memorizing these. Absolutely not. What you should be doing is understanding the process that goes into it. And really what I would do is I would look at this carefully and at the same time make sure you understand what you're doing at each stage in the specific example, because this specific example is completely capturing it. Okay, so that's completion of the square. And something I'd say as well, this is called the standard form for the function. It's the most natural way to write down a quadratic. This is called the vertex form. We'll see why in a little bit. It's called the vertex form. Now, the reason we're doing this is because this form, this vertex form, gives us a lot of power. It gives us much more understanding of the function than the standard form, generally speaking. The standard form doesn't really tell us very much, as we're going to see, but the vertex form tells us tons of stuff. So I think we should do an example. Maybe I should just write that down. The vertex form gives us lots of useful information. Lots of useful information. More useful than the standard form, as I said. Again, don't memorize these formulas, understand the process. So let's do the example I've just done from various perspectives. So let's do this example. So let's take f of x is equal to, let's do the one we did before, minus 2x squared plus 4x plus 4. I don't want to have to go through this whole procedure again because it just takes too long. You'll get plenty of practice to yourself. So when I've completed the square, I get this. It all comes out. So that's the completion of the square. Now, this tells me tons if I think about it. For example, it tells me what the range is pretty immediately. So imagine I asked to know what the range of this function is. So in this format, that's incredibly hard because I'm like, well, you need to work out all the possible values this takes. But let's remember the following. I mean, x minus 1 squared, that takes every value. Well, it takes every positive or for every non-negative value, doesn't it, as I let x vary. So that would imply, if I multiply it by minus 2, this takes every value Well, if I multiply by negative, it would become the negative numbers, wouldn't it? So it would be minus infinity to 0. 0 inclusive, of course, because x could be 1. But then if I add 6, which is what I'm interested in, that's just going to raise everything up by 6. So this would imply minus 2 x minus 1 plus 6 takes every value. In, well, minus infinity up to 6. So this is good kind of quantitative reasoning exercise. So this is going to be the range of your function. So minus 2x squared plus 4x plus 4. So that's really difficult to see, isn't it, right, in the standard form? But in this form, it's much more obvious. And we can see it up from the graph as well, right? So if I take this guy, so we took the time to graph this, didn't we? We might as well use it. So remember what the range is. The range is all possible y values that it hit, and we can see what those are pretty immediately, right? That's everything from 6 downward, which is exactly what we're getting here. Nice. Other information that's not at all obvious. What about the x-intercepts? So the x-intercepts correspond to the points where you cross the x-axis. That corresponds to the zeros of the function. So let's try and find those. So the x-intercepts, as I said, correspond to f of x is equal to 0. This is if and only if, okay, well, of course, minus 2x squared plus 4x plus 4 is equal to 0. But now this is if and only if. I write it in vertex form, it's minus 2x minus 1 squared plus 6 is equal to 0. But now this is a relatively easy piece of algebra to untangle. So this is if and only if. Let's go through it incredibly carefully. Let's take away 6 from both sides. So minus 2x minus 1 squared is equal to minus 6. Divide through by minus 2. X minus 1 squared is equal to minus 6 divided by minus 2, which of course is equal to 3. So now this is if and only if, well, x minus 1 is equal to plus minus the square root. It's going to be both, remember, because there are 2 square roots of any positive number. And finally, this is if and only if, well, you could add 1 to both sides. X is equal to 1 plus minus the square root of 3. Beautiful. So this vertex form allowed me to do this. And if you think about it, if I gave anything in vertex form, I'd be able to pull off this trick. So this really is looking at completion of the square and how it can be used to understand the graph. It's a really important procedure. Next time we're going to look at kind of properties in general of quadratic functions and how this vertex form is very useful for seeing these properties.